All right. So the last class we were discussing about the idea that what do you call it? Second, yeah. We were looking at the cubic spline algorithm for a path generation. So if we have a set of waypoints through which we want the path to be passed through, but at the same time be smooth enough, then we were looking at an algorithm to create the desired path as a function of a path variable, which we were denoting by this variable omega bar. And we were looking at the idea that this value of this, the desired path along the path variable, when omega is equal to omega bar k minus 1, must equal to the x coordinate of the k minus 1th waypoint. And similarly, if we look at the y value at the same path variable, we should get the y minus 1th waypoint's y coordinate. The same should happen when I look at omega k value. I should get the coordinates of the kth waypoint. So this ensures that continuity is there. And we next looked at the idea that even a smoothness must be there, which means that the derivatives with respect to the path variable must also match from both sides of the waypoint. We should see the same value being approached from either sides of the waypoint. We also looked at the idea that we will have a boundary condition which is either specified in terms of velocity or in terms of acceleration, but not both, because we will have sufficient number of equations to solve for the number of unknowns if we only specify one of them. And we saw that usually you can choose between them depending on how you want to give the user your choice. You can choose between the velocities or the accelerations. And the polynomial is usually given by a cubic polynomial, so where xd, the desired value of x along the path, is given as a3 times omega bar cubed plus a2 times omega bar square plus a1 times bar plus a0. It's in this format. But then when you're looking between the k and the k plus 1th waypoint, we represent these coefficients as a3k, a2k, a1k, and a0k. So given that we have points ranging from 0, 1, 2, all the way till n, and the first and the last are boundary conditions, we are ending up with n minus 1 intermediate waypoints. And for each of these intermediate waypoints, we will be having one polynomial associated with it. So thus we will have 4 times n minus 1 unknowns. And we need 4 times n minus 1 equations in order to solve this. And that is where we would formulate this set of linear equations where the constraints would be formulated as a matrix equation. So what we do is we formulate a set vector x, which is nothing but just a combination of all these coefficients for waypoint 1, 2, 3, 4 up to all the way till n minus 1. So this is all our unknowns. And this has a size of 4 times n minus 1 cross 1. Now we want to set up an equation y is equal to some matrix A times x. And this matrix A will now depend on these path variables at each of the different waypoints. So we look at what is y. Y was given by this vector which we saw here. And then the corresponding A matrix which would make sure that all the constraints are satisfied was shown to be this, where we were looking at the idea that the first 2 rows here are basically telling me that the position vectors should be approaching the same thing if I come from the left or from the right of the waypoint. And the last 2 rows, the next 2 rows were representing the velocities being matched and the accelerations being matched, so that I'm having an extreme smoothness condition within my spline so that my observed trajectory is smooth enough. So these two are matched. This is matching velocities, this is matching accelerations. And the same you are going to repeat for the next waypoint and the next waypoint and so on and so forth. At the fore and the aft, you will see these two lines which are corresponding to the boundary conditions, corresponding to omega 0 and omega n. Okay, so these are corresponding to the omega 0 and omega n. Notice that we know exactly what A matrix is. So we can take A inverse times Y will give me X. So I get all the coefficients at once. And a similar formulation can be set up for the B's as well, which means if I want to look at the values of the Y coordinates, I can do a similar approach there as well. And I should see the same come up there as well. And that's where we had left off yesterday. Okay. Any questions so far up till that point? No questions? Okay, let's go forward then. So today we'll try to understand how can we transform that path to a reference trajectory using a desired speed profile. So what we got here was a path, okay, in terms of a path variable omega prime. Okay, so we were mostly looking at the so-called path following problem of sorts. If I wanted to convert that into a trajectory tracking problem, the same approach, but wanted to change it into a trajectory tracking approach, how would we go about it? Notice that when we want to talk about trajectories, we are really more interested in the speed of the vehicle. So some desired speed of the vehicle at certain waypoints will also now start figuring into the account. Right? Because at certain points we want to be at certain times in a trajectory tracking problem. So the speed profile is particularly important, and you will see that this sort of a mechanism which we used for the path generation allows us to specify the speed profile independent of the path. So which means that if I were to ever look at an offline path planner, it can generate the waypoints and the path as well. But depending on the craft which is chosen to follow the path, based on that, I can always define the trajectory tracking problem differently based on each different craft. So if it's a small tugboat versus a very large vessel which has to follow the same path, I can choose the speed profiles differently, but the waypoints and the path remains the same. Okay. The idea here is that only the speed profile can be independently taken care of without having to worry about what the path looks like. So let's see what happens there. So this is a time independent path. That's what we saw before because it is depending on this path variable. But we can always transform any such path into a time varying trajectory by defining what is this speed profile for that vehicle. So the speed profile is basically assigning dynamics to how this omega will change, okay, with respect to time. And that is the idea which we want to bring in. So we are going to assign dynamics to this variable omega bar such that the desired path transforms into a time-dependent reference trajectory, while we are preserving the desired speed and acceleration profiles. So let's see how we do that. So we already know that if we want to take a look at this time derivative of this omega bar, then we know that that will be given by the speed of the vehicle divided by square root of x desired slope, so derivative of that square, plus y desired derivative square. We have seen this formulation before. Notice here that what we are saying here is I will specify this ud of omega differently for different vehicles. Depending on the vehicle, I will specify the speed profile. If the vehicle can't make sharp turns, I will specify a slower speed profile. And if the vehicle can really make sharp maneuvers, I can go for higher speed profiles. So the path remains the same, but just that how the path variable is changing over time now makes a difference. That will determine how fast we move along the path. Is everybody following me there? Yes? Okay, excellent. Okay, now when we actually are looking at an implementation, a practical implementation, we might actually be interested in this desired path, this desired value along the path variable to be governed by some first order differential system where I am saying this UD will vary very slowly depending on my input of uref. So the idea might be that, let's say that I have given n waypoints and I want to track a path through these n waypoints. Not only just track, but I want to specify waypoint 1, I want to cross with the speed of u1. Waypoint 2, I want to cross with the speed of u2. And waypoint 3 with a different speed, so on and so forth. Then what I can do is I can specify the moment that a transition happens from waypoint k to the next waypoint k plus 1, I can specify this uref as uk plus 1 as an input, and whatever that I am getting as the output, the desired speed, which is slowly varying and going to approach that uref over time, that can be my speed profile in between the waypoints. So let's say that I'm starting from waypoint k and I'm going to waypoint k plus 1. Okay. At this point, my speed is, let's say, uk. And at this point, I want my speed to be uk plus 1. So the moment I am reaching here and I am undertaking this path, I'll specify my desired speed across this trajectory is given by this differential equation which you see here, where t is a time constant, ensuring that over time I start at some value uk and I reach some value uk plus 1. Write this better slightly, uk plus 1. Okay. So it starts here and I want it to stabilize something like that. Okay, and that time constant that I am choosing as to how fast the speed can change really depends on the craft dynamics. If it's a very small vessel, maybe I can choose a much slower time constant, but if it's a very large vessel, I may be required to choose a much larger time constant. Is that making sense? Yes, no?
Yes, sir.
Okay. All right. So the idea here is then that there is a smooth transition in the speed from uk to uk plus 1 using this first order system, where this t is our design parameter, which is governing as to how slowly or how quickly this change is happening. Notice that the advantage of this method is the path does not necessarily need to change. Only, so suppose during the implementation phase, instead of one vehicle, some other vehicle is being used, we can always use the same path, but we can now parameterize it in terms of a trajectory tracking problem slightly differently, depending on the speed profile being provided for that craft. Okay, so we can play around with this time constant and we can give out a speed profile which matches the dynamics of the craft. All right, so this was a very easy way to see how the how to do a waypoint or how to generate a waypoint through different specified waypoints, how to map a path, how to plan a path, especially a curved path through these waypoints. We'll take a look at one other method which is also quite popular, but it is a little more computationally intensive as compared to the current method that we have seen. And that one is trying to use nonlinear constraint optimization methods to solve this problem, to figure out what should be the path. Notice that this is definitely harder to solve numerically, and it usually requires some sort of a optimization toolbox or optimization methodologies to be programmed. And we'll look at only one such simplified version of it, which is called quadratic programming. And we are not going to delve into how quadratic programming problems are actually solved, but we are only going to set up our problem as a quadratic programming problem, and we'll use typically some Matlab or some standard toolboxes to set up the problem and solve it in order to get our trajectories or paths. So a general trajectory tracking and a path planning problem can be expressed as some minimization of an objective function which is subject to some constraints. So these constraints can be inequalities, which I'm representing by G in this case, or some constraints could be equalities, which I'm representing by H, and then there could be a range of values which your inputs can take. Not all possible values might be taken as inputs. There may be certain range beyond which you can't go. So for example, let's say if it's a rudder angle, we know that it is limited to between minus 35 and 35. I can't say 90 degrees rudder, that makes no sense physically. Okay, so such limitations will exist on your variables as well, which are specified in terms of these inequalities. So the idea is that this is actually a nonlinear optimization problem. This is a generic nonlinear optimization problem. Okay. I can specify it in a little simplified manner by expressing this J as 1/2 of X transpose H times X plus F transpose times X. So if I can represent the objective function in some such sort where this function needs to be minimized with respect to these inequalities, matrix inequalities, Ax is less than equal to B, and some inequalities on the different variables, then such a problem is called a quadratic programming problem. Okay? These sort of programming problems can be solved effectively. There are methodologies to solve them, and there are different methods as well. They're not just one methods, but multi-methods in order to go through them. Now, we are not going to look at what are the methods to solve that problem. Our interest is only in formulating our problem into this quadratic programming paradigm, so that then we can use standard solvers in order to make this happen. Hopefully, we'll set this up as one of your assignment problems where you can get a feel for it, where you can set up the problem as a quadratic programming problem and use Matlab's optimization toolbox in order to solve it to come up with a trajectory tracking problem or a path planning problem. Okay, so let us say, so in order to set up our problem in this format, let us say that there are two waypoints, xk and yk plus 1. Okay, so kth waypoint and this is k plus 1th waypoint. Now we know that at time tk, this should be the two coordinates. At time tk plus 1, this should be the two coordinates of the points. So choosing the speed constraints as x desired dot is equal to uk times cosine of ik, where ik is the angle between the first waypoint to the next waypoint. Right? This is the course angle between the first waypoint to the next waypoint. We have seen this before, so this should not come as a surprise. Similarly, y desired dot will be uk times sine of kk, where kk is this angle given by a tan 2 of yk plus 1 minus yk divided by xk plus 1 minus xk. All right, now for two waypoints which are taken as k and k plus 1, we can set up a matrix equation for this where we are trying to make sure that the speed and the position profiles are matching between them. So at time tk, we know that the value of the coordinate x coordinate is xk. At time tk plus 1, it is xk plus 1. The y coordinate is yk, y coordinate is yk plus 1. Similarly, the speed at time k is given by this, y speed is given by this, x speed at waypoint k plus 1 is given by this, y speed at time tk plus 1 is given by this. Okay, these quantities are known to us in a trajectory tracking problem, right? Once we have the path and the trajectory, we know this idea that technically where we want to be. In fact, the problem is we don't know the time tk plus 1. We know that I'm starting at some waypoint tk, but my objective is to formulate a trajectory tracking problem. So I need to know when I should reach tk plus 1 as well. Okay, so tk plus 1 is an unknown here. Okay, so let us say that now I want to set up this as a matrix equation. Okay, so I know the positions of the waypoints, so these are known. So then chi-k will be known, because once I know those waypoints, I can precisely specify what is chi-k, and similarly I can find out what is chi-k plus 1 as well. Okay. Now, the speed at each of those waypoints, or the desired speed at certain waypoints, is usually provided as an input, which we can take. Now the idea is we want to specify how much time it should take to go from one waypoint to the next, and how is the smooth trajectory being formulated as a function of time. So we set up this matrix equation y is equal to, which is consisting of this vector which is known to us. So notice that y is known. And at that I'm able to set it up as a cubic polynomial of x, where x is basically the set of coefficients. So you can think of a3, a2, a1, a0, right? Should be a2, and then a1, k plus 1, and a0, k plus 1. So I have this. This is my x vector. Okay, so that being my x vector, I'm trying to formulate what should be my A matrix. So I know that this first polynomial multiplied by a3 times tk cube plus a2k times tk square plus a1k times tk plus a0k times 1 must equal to the x coordinate of the waypoint. Correct? So that I know that's going to be definitely taken care of. So similarly, I know that the same should be applied for when I multiply this with the next one, these next three, right? Okay, wait a minute. Let me just make sure that I'm talking this correctly. Oh, right. Okay, sorry, my mistake. X here is not that. We are not assuming we are assuming a single cubic spline through all of this, because we are trying to find those coefficients through quadratic programming. We are not looking at individual quadratic programming. Okay, so this is simply A3, A2, A1, A0, B3, B2, B1, and B0. So basically, I'm just formulating a cubic spline which is looking as x is equal to a3 times t cube plus a2 times t square plus a1 times t plus a0, and I'm formulating y coordinate as b3 times t cube, b2 times t square plus b1 times t plus b0. Okay, I want to find out these coordinates, these coefficients a3, a2, a1, a0, b3, b2, b1, b0. That's what I'm trying to do. That when I substitute t equal to tk, I should get the value as xk. When I substitute tk plus 1, I should get the value as xk plus 1. When I substitute the value of tk and I look at the y coordinate, which means I'm looking at the b coefficients, I should get yk. The fourth row here, you see that when I look at tk plus 1, I should get the fourth element here, yk plus 1. Is everybody with me so far? Yes?
Yes, sir.
All right. Now, these last four quantities are the differentiation of these things so that I can get the velocities. So I know that this is simply the 3 times tk square plus 2 times tk and 1 comma 0. This is basically they're taking the derivative with respect to time. These are the coefficients which will be left. So when I multiply this with the a terms, I should get the x velocity at point k. That is what is this fellow. The next one, I'm taking the y velocities. I'm multiplying these with the b coefficients. So I should get the y velocity at point k. Similarly, I do this and find the velocities as k plus 1 as the last two rows. You'll see that instead of tk, now I have tk plus 1 in these two rows. Okay, so I'm just ensuring that the positions are matching and the velocities are matching to the desired velocity profiles which I have created at that particular waypoint. In between how they are varying, they'll be determined by the fitting that I am doing. Okay, so there are 9 unknowns in this problem. We do not know A3, A2, A1, A0, B3, B2, B1, B0, and we also do not know tk plus 1. Everybody with me so far? Okay, so this is a problem where I'm trying to solve for 9 unknowns through quadratic programming. Okay, and then there might be some constraints which might come into the picture, that the speed can't be more than this, and those constraints have to be formulated into your a times x is less than equal to b sort of a format. Okay, once you set up this problem, you can give these as an input to your quadratic programming solver. Okay, there is actually a quadratic programming solver in Matlab, which is called Quadprog, correct? Okay, and this can actually take in your setup problem, which you are providing it, and then it will try to evaluate a solution for it. But before I do that, we need to give it what is the objective function and what are the constraints. Okay, so let me just formulate the objective function precisely and we'll come back to this. So our target here is to minimize this difference between a times x minus y. So what I'll specify this value of j as is a times x minus y transpose times a times x minus y. So I want to minimize this value and I want to find which x will minimize this, and that is the x which will give me the coefficients which will determine the trajectory. That is the idea. If I expand this out, you will see that there will be some terms in this objective functions which are constants, which don't have anything to do with the variable x. So those terms I can kind of try to separate them out, because you see you will get one term which is called y transpose times y. Y transpose y is a fixed value. It doesn't change, right? Y transpose is these quantities which are known quantities. So there is nothing which will change in this as x changes. So therefore those things can be taken out of your objective function. I can write down my new objective function as 1/2 of j minus y transpose times y. And you'll see that this is what I get out of that. Now if you compare this with the quadratic programming approach which we had seen before, you'll observe that in that quadratic programming, that H matrix where we had half of x transpose H times x, that H is nothing but A transpose A in this particular problem, and we had the case where we had F transpose times X, which in this case will be minus Y transpose times A. Okay. It's just a question of identifying what is the components of your quadratic programming solver. So you have to provide these as input to your the value of H and F. You'll have to provide them as an input to your quadratic programming solver. And then it will try to basically evaluate the constraints and make sure that it can come up with a value of x which best satisfies this constraints. Okay. Typically, we can use like a, as I said, optimization toolbox, and we will try to set up an assignment where you'll use quadratic programming in order to solve this problem to come up with a set of waypoints. Okay, so please wait for your assignment. There you might be able to see more of this in action. It will be much more clearer then. So this is a different methodology as compared to the previous methodology of cubic splines that we had seen. So we had seen cubic splines as one of the methods, but that's not the only method. There are other optimization methods also which can be used. One such example is quadratic programming that we have just seen. Okay. Doesn't necessarily mean that you can't use other optimization routines to solve for a trajectory tracking problem. You can use any of the optimization methods which you require, as long as you can set it up as an optimization problem. But the point is, the more complex the optimization problem, the more time consuming or more computationally intensive it becomes. And for a real-time application, you want to keep it as simple as possible, typically. Okay. As much computational effort can be minimized, the better it is. Everybody with me so far? Yes? All right. Okay, so now we come to the last portion of our discussion on guidance, which is we will now talk about, we had looked previously at the proportional line of sight guidance law for straight line paths. We'll now simply extend it to curved paths. So we so far talked about, whenever we talk about the curved paths, we are talking about how to generate the curved paths is what we have discussed so far. Now we will discuss about whether our controller which we had, the so-called guidance law which we had prescribed for a straight line, is it still applicable for our curved paths is what we are trying to look at. Okay? And you'll see that there is some challenge. In fact, it is not so straightforward. Okay? And it does make the problem a little nonlinear, and let's discuss about it. So notice that in the proportional line of sight guidance law, we had the course angle, the desired course angle was given by the angle pi p, which was the angle of the line joining the two waypoints with respect to the north, minus tan inverse of kp times ype, where ype was the cross track error and kp was the proportional gain. And this gain was typically specified in terms of the look ahead distance as 1 by delta. Okay, we had seen this before. Now, let us say that we have a curved path and we are denoting that path in terms of some path variable omega bar, which is greater than or equal to 0. Okay, and this path passes through the different waypoints that we have in place, and we are considering that it is moving from waypoint I to waypoint I plus 1. Okay. Now, we want to figure out that suppose my craft is at this location currently, which is denoted by, let's say, xn, yn. Okay. I want to figure out what is the closest point of approach. So where should I place my origin or the path tangential frame? I want to find that out, right? xp and yp. And then basically our interest is to figure out this ype. Once I know that ype, I can plug it in here and then I have everything I need to get my guidance law done. So that will give me a desired course angle which I need to follow. But the problem here is to find out ype is not as straightforward as it was before. Notice that because the parameterized path is assumed to go through the successive waypoints, when we are now considering that so-called angle pi p, it also is a function of the path variable omega. When the two waypoints we were just looking at straight line between the two waypoints, this was precisely known. We exactly knew what pi p was. But whereas when we are looking at a curved path, pi p is no longer constant, but it's actually changing over the length of the path. Is that making sense? Right? Okay. Now, that pi p can be expressed as a tan 2 of yp prime divided by xp prime. Okay, which means I'm taking a derivative of this with respect to the path variable omega bar, and then I'm taking a tan inverse, and that should give me the local path at that particular point. Notice that we do not know where xpn and ypn are to begin with. because I do not know. In the previous case, we were having a straight line, and I simply had to, where is my pointer? Okay. So if my graph was here, I had to simply drop a perpendicular, and that is the point at which I was. That was the along track distance I had moved, and I could actually mathematically calculate it. But here, when it is a curved path, we do not know where are these 2 points actually to begin with. How to determine that point becomes a challenging aspect to deal with. Okay, for a straight line case, as I said, we exactly knew this value, so therefore, because that was a constant. But now, when we have a graph which is located at a distance x and y and coordinates, I can write down the same equations, but the only difference is now this pi p is unknown to me ahead of time. Okay, in the previous case, I exactly knew that pi p because it was the 2 waypoints were precisely known. Here I do not know pi p. I actually need to find out along the track of the path how far have I progressed, and based on that I have to make sure that I can find out where my x and y locations for the path tangential frame are located at. Once I know those points, yes, I know pi p, and then I can actually go ahead and calculate my cross track error. Okay, but I don't know it ahead of time. So if I look at these 2 equations and I try to look at the top equation, I actually see that it is an equation of the normal to that path. So if the path is looking something like that, and at this point this is the tangent, then I'm looking at a line normal to it. That is what this equation is telling me. It's an equation of a line which is normal to that. Right? That's why its slope is -1 by tan of pi p. Okay. All right. That second equation gives me an expression for YPE, which is the cross-track error. Now, the idea here is that where omega exhibits a dynamics, which is consistent with the speed profile, which is specified as omega bar dot is u divided by square root of, there should be a prime here. I think there's a mistake. Okay, so x p and p prime and y and p prime squared, added up, taking the square root of it. Now, if I am looking at a closed curved path, so which means that I start at some waypoint and then again I'm ending at the same waypoint, then there could be multiple paths that I can do. Right? There can be multiple paths which may be possible, which may be going through it, and depending on where my craft is located, it will be very hard to pinpoint which path am I actually on. Right? So it's actually known that for a closed curve path, there may be infinite solutions of this first equation, which will satisfy that constraint. So therefore, we may not be able to figure out where exactly is our path tangential frame's origin. It's not a unique problem to solve. So therefore, we will assume that our path is open path. Okay, and that is without loss of generalization, because any closed path we can think of it as two combinations of open paths. So that's well and good for most of our purposes. We just need to add an extra waypoint in it if we really wanted to make sure that we wanted to find out where this is. Okay. Now the idea is, when it is an open path, a unique solution for YPE, or the cross-track error, is obtained by minimizing omega bar dot. So it can be shown mathematically, and we are not going to prove that mathematically in this course right now, but mathematically it has been shown that we can find a unique solution for YPE for an open curve by minimizing this value of omega bar dot. So if I look at this omega bar let's say that the unique solution is denoted by ype at omega star, okay, then that omega star is the argument which will minimize this function u square divided by xnp prime square plus ynp prime square. Okay, and that proof of it we are not really looking at it in this particular course. Okay, we are now delving into mathematical geometry, and I don't want this to convert into a course on mathematical geometry. So you'll have to believe me for that purpose. Okay, or if you're really interested, I can point you to the reference where you can look back and figure out how that proof has actually come back. But it can be shown that as long as I'm on an open curve, a unique solution for YPE does exist, and that is obtained by choosing the value of omega as an argument which will minimize this omega bar dot, subject to the constraint that the point xn yn lies on the normal line to the curve. Okay, we want to make sure that the normal of that, wherever the point is chosen on the path curve, if we draw a normal curve to it, our graph should lie on that normal line. Okay, only then it can be a path tangential system, right? Is everybody following me? Everyone? Anand? Following me?
Sir, I lost you.
So why won't you speak up? That's why I'm asking you to tell me if you understood or not. All right. The idea is, let's say that I have a curved path, okay, and I'm looking at a graph. I want to construct a path tangential system. So I need to look at a point at which the path is tangent and the normal is passing through the graph. Correct?
Yes, sir.
Right? So that is the constraint which is specified by this equation, right? It's specifying that this point xn yn, which is where the graph is located, lies on this normal line. This line is nothing but the equation of this normal line, given that I know where this point is. Correct?
Yes, sir.
The challenge is there may be multiple such points. In a curved path, there may be multiple points where I may be able to draw a tangent, and such that the normal at that point will actually pass through this one. So let's say, for example, let us say, okay, so let me try to see. So let's say this is my point. The path is tangential here, and the path is also tangential here, let's say. Say the path looks something like that. Okay. At both these points, I can actually make sure that the path, this is the point xn, yn, that is where my craft is. So my xnp of omega bar could be either here or it could be here. I have to find out which one is it that I'm corresponding to. Right? The idea here is that as long as this is an open curve, then I can try to minimize this value. Okay, find the value of omega which minimizes this value, and that will lead to me to the right value of the x and y coordinates of the path tangential frame's origin. I want you to understand the idea. The question of why I have not answered. Okay, I'm just saying that mathematically it can be shown that that is the case, but I want you to appreciate as to what am I saying actually. Everybody with me now? Okay,
Yes,
so as long as I can minimize this value, the value of omega which minimizes this value, which is nothing but equal to omega bar dot, okay, then I can find a unique solution for this cross-track error. So once I know the point xnp omega bar and ynp omega bar, I can precisely find out what is the cross-track error. After I find the coordinates of this point, it's not very difficult for me to find the cross-track error, and the expression is actually right here. Once I know where the coordinates of these 2 points are, I can precisely find out what my cross-track error is. Okay. In case of our waypoints where I was looking at a straight line path, it was much more easier because pi p did not vary with time there. And I could precisely know the point where the origin of that path tangential frame would be. It would always lie along the line connecting the 2 waypoints. Whereas here it need not. So there may be multiple possible solutions. And the idea is that it's becoming a nonlinear optimization problem that find the value of omega bar, which will minimize that value of omega bar dot. And at that omega bar value is your origin for your path tangential frame, based on which you now construct the cross-track error. Everybody with me so far?
Yes, sir.
Shadab, yes?
Yes, sir.
All right. Now, that is the only difference here. So it now has turned into a so-called nonlinear optimization problem, which has to be technically solved using numerically. But many a times we can actually just figure out what are the possible points at which the path can be tangent to the line connecting the perpendicular from the graph to the curve, and we can choose those candidate points and simply evaluate where is the value of omega bar dot minimum, and then simply choose it. That might be one easier approach to get by, but in typical sense you still have to look at a nonlinear optimization problem. And this problem is coming because we do not know the angle pi p precisely ahead of time. When we were looking at straight lines, we precisely knew that angle ahead of time. Okay. But the same process of our LOS guidance scheme still works, but we only have to identify that location of our path tangential frame and then apply our LOS guidance scheme to figure out what is our desired course angle. So the approach still works for the curved paths as well, but the only challenge involved is to find out where the path tangential frame's origin is at any particular time. Okay, everybody with me so far?
Yes, sir.
All right. Okay, so with that, we basically come to an end of our discussion on guidance systems. So just to summarize, what all did we see? We looked at the idea that we started off with the trajectory tracking problem, then we looked at the target tracking problem, and then we looked at the path following problem. So these are the 3 things which we started looking at. And then in the path following problem, we specifically focused first on waypoints and straight line connecting the 2 waypoints, and what are the different guidance schemes available to us in order to tell me what is the desired course angle that I want to follow. We looked at the vector field guidance law. Then we looked at a special case of that, which is our look ahead proportional LOS based guidance law, where the only idea difference was that when I was far away from the path, I would be coming perpendicular to the path in the proportional LOS scheme, whereas in the vector guidance field, I can specify at what angle I should be coming at. Okay. Then we looked at the ideas of what you call enclosure based LOS scheme, and we understood that the proportional LOS scheme based is better than the enclosure based LOS scheme because that requires us to choose a radius big enough so that the circle actually intersects the line connecting the 2 waypoints. Then only we can find a guidance value. If we choose the R to be too small enough, that methodology does not work. Whereas the look ahead based, distance based LOS scheme always works no matter what the situation is. So that is a better approach to look for. And no wonder that was the more popular approach for missiles, and that has become the norm nowadays. You don't see much happening with enclosure based LOS as much. Then we looked at the idea of curved paths, how to generate curved trajectories given a set of waypoints, and how to plan a path through them. And then we figured out how to follow that path is what we discussed today using a proportional LOS guidance scheme. Okay. So these are the different methods which we have looked at, particularly with respect to the guidance technologies. Now, there is a lot more to it. We have only scratched the main surface. Please understand that there are more complicated guidance schemes as well. But again, as I said, complex is maybe mathematically elegant many of the times, but what works in the real field needs to be made simple many of the times. Okay, so it's a balance between the two of them. You may come up with a very beautiful, complicated Lyapunov function and can demonstrate what you call excellent stability criteria, but it might be just practically not implementable where I want to look at, let's say, fourth derivative of the torque or something like that. That may not be something that I may be able to actually control. Right? So we have to make a balance between what is practically implementable and at the same time what is going to help us achieve our target tracking approaches. Okay, particularly if you remember, we looked at the idea of integral line of sight control, and we saw that when we include the integral term inside the tan inverse, finding that gain can be quite a challenging task. Okay, so therefore that is why we went ahead with a revised integral line of sight scheme, which was non-linear in sense, but at least it gave us some stability properties. So I'm kind of trying to push you to understand that more complex is not necessarily always better. We want to make things as simple as possible, but sometimes what we want, we have to be very clear about. So stability is something which is of very important concern to us, in which case we may be inclined to go for nonlinear methods in lieu of linear technologies. Okay. Now, next class onwards, we'll start discussing about control. We'll mostly first focus on PID control, where we'll be looking at the ideas of proportional, derivative, and integral control for linear as well as nonlinear systems. Okay. We'll start off with the linear, which most of you must have seen in your what you call maneuvering and control of marine vehicles course, but then we'll kind of move off and try to discuss about the nonlinear control using PID methodologies as well. And that is where we will leverage our Lyapunov methods, which we have studied so far, in order to prove stability and see that how they can help us at some of the nonlinearities of our vehicles crafts, how those dynamics can be helpful for us, especially in designing controllers. So once we are through with the PID, we probably will have some time left and we may be able to explore LQR control as well. Okay. If time really permits, we will take up backstepping controller as well, but I have serious doubts that we'll have sufficient time to get to that point in this course. Okay. So we'll try to see if we can make it work. Some other topics which we could not cover in this course, okay, was navigation systems. So what we could not cover here is Kalman filters and any other state estimation algorithms where we are measuring certain things from our sensors. So our sensors are not measuring the exact thing which we want. So we have to compute the things which we want from the measurements which the sensor provides us. How to do that, how to do the state estimation is something which we have not really discussed in depth in this course. So these are things which are left further and one can definitely delve more, and your textbook is more than sufficient to cater to these needs if you're really interested in them and taking it forward. Okay. I know that we may not be able to succeed in going for a field trial all the time, but in any case, since most of you are on campus, and whenever we are planning for any field trials with our ASVs, I'll definitely try to involve all of you together. And I want to kind of see that this actions of what we have studied with respect to guidance and control should come to play in testing these vehicles out in the field. Okay. All right. Let me stop recording then. If unless there are any questions. Are there any other questions? Okay.